Our next lecture is a plenary lecture given by Professor László Lovász, who is a full member of the Hungarian Academy of Sciences in the mathematical section, and who is also the recipient of the Abel Prize for Mathematics in 2021. And his talk is Discrete or Continuous Mathematics. Laci, please.
So, happy birthday, Hungarian Academy of Sciences. I will steal a couple of minutes of my time because I would like to add something to the many things that have been told here about the history of the Academy. Maybe it was told and I just missed it, but since the restoration, for example, of this fantastic room was just finished, I think I would like to tell you that this building of the Hungarian Academy of Sciences, which is still not fully restored, but it will be much more glorious when it will be fully restored. So this building was not donated by the king or by the Kaiser. It was built completely of public donations. And 10 years ago was the 150th anniversary of the completion of this building. And at that occasion there was an exhibit, and this exhibition, there was the sign-up sheet for these donations were visible. And there was this one sheet where, for example, there was some rich nobleman giving probably 70,000 forints. That was a huge amount of money at that time. And then the next line was a servant girl giving 5 pennies. And that was really moving. I mean, this really showed the joint forces of the society in order to make the Academy really happen and really give it a house which it deserves. And I think that ever since then, the strength of the Academy was that it was supported by the society. And of course it was supported by the society because we scientists, even though some of us are religious, some of us are not, some of us are more right-wing, some of us are more left-wing, but we unite in the support of science. And this particular event, so I would like to thank in particular now our external members who organized this and gave generous donations in order for this event to happen. Thank you all, and I think this is also one of the signs that Hungarian science is strong, living, and it unites the scientists. So let me start with my talk. Let me go back to the ancient times. So Zeno's paradoxes. And for example, there is the most well-known is probably Achilles and the tortoise. Can Achilles catch the tortoise? Achilles runs 10 times as fast, but the tortoise starts earlier. And Zeno argued that Achilles will never be able to catch the tortoise because by the time he reaches where the tortoise was when they started, then the tortoise has already crawled further. So Achilles has to get to that time, to that place, but then the tortoise had already got further and so on. so he will never catch it. Now, there are many explanations for this, going back to Aristotle, but I think it's about one possible explanation, or it says that there is problem with the idea that time or space are quantized, because then this argument really works. Of course, we don't know whether time or space are quantized, so this is still debated today, and there are, because matter is more or less, we know it's quantized, it's discrete, while space-time is continuous. And there are all sorts of questions actually bothering me too, that, for example, if space is continuous, then there should be a meaning that the photon has an interaction here and an interaction here, and then at some point it's halfway. Now, what does it mean it's halfway? I don't see any meaning for that. But anyway, that's not my area. I just wanted to point out that continuous and discrete are really two different notions. And in fact, it seems in mathematics that there are really two kinds of mathematics. Continuous mathematics, continuous in this setting means it's without interruption, like the whole real line has no interruption. Discrete, and mind, it's not the same as discrete in everyday sense. It's a structure which consists of separated, well-distinguishable elements, usually a finite number of them. The application areas are also rather different. Continuous mathematics is, of course, the basis for classical physics, mechanics, Maxwell's equations, and so on, engineering. Discrete mathematics, however, got a lot of new impetus and new problems from computer science, from genetics, from telecommunication. But it still looks like they have very different application areas. And it's even more so if you think about basic notions and methods of these areas. In continuous mathematics, we have this great wealth of tools from classical analysis, real function theory, the notion of convergence, notion of differentiation, series expansion, solutions of differential equations, and so on. These are all very powerful methods used all over the place. Now, discrete mathematics, which has a later start, like Achilles, has notions like graphs, Boolean functions, counting, uses induction all the time, uses tricks like inclusion, exclusion, and speaks about the information content of some string, like a DNA string, and entropy, and so on. So the notions are different and so it seems that really mathematics has branched into two areas, and well, we have to live with it. I don't think it's true. Now, of course, if you have some continuous object, you often need to make it discrete in order to do computations or maybe to create pictures on your screen. And that is used all over the place, both in computer science or computing, I should say, and in algebraic topology. Let me make a slightly less obvious example, where you approximate discrete by the continuous. So let's look at a piece of steel. Is it a discrete object or a continuous object? Well, we all know that it consists of atoms, probably more or less a crystal of atoms, arranged in a nice, regular way. And so it's a discrete object. But if an engineer wants to do something, then engineer cannot work. It's impossible to write up all the equations of quantum mechanics separately for every atom and solve this system. So the engineer has to approximate this, consider this as a continuous object, and then he can use, and then there will be certain functions on it, like density, pressure, temperature, and the engineer can write up differential equations for these and solve them, and that works. That's a valid method because we have bridges and machines and everything, automobiles. So here you have something which is discrete, and you approximate it with something which is continuous in a successful way. In fact, if you would like to create like a piece of steel which is a more complicated structure, like, for example, this dolphin, you want to make it out of steel, I don't know why, but let's assume you want to make it, then you think of atoms, then you approximate it by a continuous material. The shape itself you then describe by a continuous surface, and then you discretize this continuous surface. So you are actually moving back and forth between these two words. Let me illustrate the basic difference between the two words by an example. So it's a problem, a high school problem. What is the minimum of the function x cubed minus 6x in the domain x greater than or equal to 0? So it's somewhere here. You probably have already computed, everybody, what is the answer. The solution we learn in high school is that you take the derivative, easy to compute, you solve the equation derivative equals 0, and you get that x is square root of 2. And the value of the function is minus 4 times square root of 2. So this is all very classical. Let's see a discrete optimization problem. Borůvka, a Czech mathematician, in 1926 got started to solve the problem. He wanted to optimize the Czech electrical network when it was being built out, finding the cheapest way to connect every city, so make a single connected network. This is, of course, will be some kind of tree-shaped. Actually, we call it a tree. The network itself is modeled by a graph on n nodes, where the edges, in addition, we know how much it would cost to build that particular edge. Think of it more or less as the length of the edge. So this is a graph. Actually, I will use graph and network sort of interchangeably. So you can think of it as a network. And then there is a greedy algorithm, it's called, which says that build these connections one by one, always choosing the cheapest that is not built yet. In fact, the cheapest which increases connectivity. So if some 2 points are already connected through some maybe detour, then you don't connect them, even if it's cheap. And just based on this algorithm gives the exact optimum, and that's a theorem. It's not obvious, but it's a theorem. Now, why is it not obvious? Let me come up with a problem which actually lives nowadays, and it's a very important problem in computer networks. I, of course, can only show a very simple special case, which is very far from real life. So you have some servers. These are the red nodes, and some clients, which are the blue nodes. And not everybody is compatible or can be connected for whatever reason with a server, but there are these connections. And we would like to assign servers to clients. Ideally, every client gets assigned to a server. Now, here I am simplifying because I assume that a server can only serve one client. This one client could be maybe 5 million, but nevertheless, there is a capacity there which cannot be exceeded. Now, this problem was solved in 1931 by Dénes König and Jenő Egerváry, and we are celebrating the 200th anniversary of the Hungarian Academy of Sciences. So let this be also a contribution to this, to the history of the Hungarian Academy of Sciences. So, and they came up with an answer to this. König gave a kind of description or characterization of this. Egerváry gave an algorithm under a little bit more general circumstances, but certainly covering this. And it's still called the Hungarian method in textbooks. So this is should be mentioned here. The greedy algorithm would not work here, so it could lead to suboptimal pairing or assignment. And there is a more complicated but still efficient, technically it's called polynomial time algorithm to solve this. Let me talk a little bit, because here already the approximation of the discrete by the continuous comes up. So in order to be able to draw, I have simplified the network just to these 4 nodes. And now, and on top there are listed all the possible assignments of servers to some of the clients. And they can be described by, sorry, I wanted to push. So here, these equations say that you can describe each of these biological variables. So if the edge 1 is used to serve a client, then we write x1 equals 1, otherwise we write x1 equals 0, and so on. And then the goal to serve as many clients as possible is given by adding up these 3 variables, x1, x2, and x3. And there are conditions on these x1, x2, and x3. They have to be non-negative. And a server can serve only one. So like x1 plus x3 is at most 1, saying that the top red server cannot serve two of these. So you have a system of linear inequalities, and you have a linear function, x1 plus x2 plus x3. And so you have the task of maximizing a linear function subject to linear constraints. And here is a big thing. I mean, that is a problem which has attracted a lot of time, a lot of interest, and people have for a long time. Let me just mention that the basic lemma in linear programming is due to Gyula Farkas, again celebrating our 200th anniversary, but it's called the Farkas lemma in textbooks, so that's there. And then, of course, Danzig and Kantorowicz, and since then many others have developed applications algorithms. So linear programming is a big and rather well-solved area. So here are these inequalities, but now this is an important but technical but important detail, that to these inequalities we should add the condition that x1, x2, and x3 are 0 or 1. And that you cannot express by linear inequalities. You can express it by a quadratic equation. Say x1 squared equals x1, that characterizes 0 or 1. However, if you add this, then you will get into the realm of nonlinearity, and everything blows up. So it doesn't work either. Nevertheless, this particular problem can be solved, and in this particular case, actually, it turns out that this 0 or 1 condition will be automatically fulfilled, but I will not go into these technical details. So let me come to another aspect of connection between approximating finite discrete structures by continuous. And let me start with observing that the very large networks play a central role in science today. It used to be said that the language of science is differential equations. I think now you should at least add that it's networks. But network theory is much less developed than analysis, and so that makes it challenging and interesting. So here I have listed a few of these networks, internet, social networks, and so on. These are all huge, billions or 100 billions the universe is a huge network of elementary particles, so that's really the largest of these. So this is a new mathematical language of science, and we have to answer a number of basic questions. What can mathematics say about these huge networks? Let me give you an example. A classical mathematical question about graphs, a basic mathematical question about a finite, nice small graph, is whether it has an even or odd number of nodes. That influences its properties quite substantially. However, if I ask you whether the internet has an even or odd number of nodes, then this is a ridiculous question. Obviously, the internet will never be known to that degree, even defined to that degree, because at any time we look at the internet, there will be places switching off, switching on, and so on. So this is an example where, with these large networks, we have to think in entirely different terms if we are bound to understand their properties. How to obtain information about them? Again, they are too big, and in addition, never exactly determined, because they are usually changing a little bit all the time. But if you think about, let's think of social networks. So these are networks which are, for example, let's think of all people living in the earth, and the edges of the network mean that those people meet last week or whatever, at some particular time. This network has played a central role in trying to understand and predict the propagation of COVID-19. And so people have developed methods to try to get information about this network, which cannot be described entirely. People have sent out forms asking people, how many people have you met last week? Now this is a test, a kind of statistical test of this network. You pick a random node and you try to see how many edges go out of that node. And then there are sometimes more complicated questions that people have put on these questions or calling on telephone and so on. So there are ways of obtaining information, never a full information, but it turns out sometimes sufficient information to be able to say valuable things. And then it's very complicated to run algorithms on them. You will never be able to put the whole network into a computer, so you have to do the algorithm also on a kind of statistical basis. And how to model them. So you want to construct something which you can put in the computer, maybe a scaled-down imitation of the internet or of the social network or either one of these. I mentioned the COVID preparation. Now it turns out that, again, celebrating our 200th anniversary, running algorithms on these large networks, at least if they are dense enough, the key, really key tool is the regularity lemma of Andres Emerédi from 1975, which was an important part of the citation of his Abel Prize. Now, one way to model a large network is use a random graph. So, and here the basic object is what's called the Erdős-Rényi random graph, which they started to study in 1959, and they developed that theory, and that theory was further developed by many other people. There are now monographs and conferences and journals devoted to random graphs, very fundamental thing that happened. So what is a Erdős-Rényi random graph? You have n nodes, and you connect any two of these nodes with probability p independently for different pairs. So random graphs have been proposed to use so these are two parameters. N is very large usually, and p is something, could be 1/2 or 1/3. Now, it has been proposed to use these to model the internet or other objects, but there was a fundamental problem with using random graphs for this purpose, because now I have to get a little technical. If you look at a node of a random graph and you look at the degree, the number of edges going out of that node, and you look at the distribution of these degrees, then this distribution will be the standard Gaussian distribution, the bell curve, highly concentrated. The larger the graph, the more concentrated around the average, which would be p times n. However, in real life, the distributions are not like that. That has been recognized already in 1930s, I think it's called in social sciences, the Zipf phenomenon, which says that the degrees have a heavy tail, so they are not highly concentrated, but they have much more slow drop as the parameter grows. So the degrees would not correspond to the degrees of Erdős-Rényi random graph, and motivated by this question, Albert László Barabási and Réka Albert, both external members of our academy, came up with a new model. It is at every step a new node is born, and this new node selects some number of previous nodes with probability, and then it connects to those with probability which is proportional to their degrees. So it's more likely to connect to a higher degree node. It's some kind of snobism. That if that person knows many other people, then I want to know him. And it turns out that this phenomenon gives rise to this kind of much slower drop in the distribution of the degrees. And it seems that there is, we all learned that in probability theory that in real life every distribution is Gaussian or approximately Gaussian because it's a sum of small independent random variables, many independent random variables, and that's indeed means that it's Gaussian. But here there is a kind of positive feedback, and positive feedback leads to this kind of phenomenon. So this is modeling. Now let's get another question: how to visualize these very large graphs. Here are a few pictures which I found on the internet trying to visualize the internet. I have to tell you, I don't think either one of these gives any useful idea. Let me propose another way of visualizing a graph, possibly a large graph. So here is a traditional way of drawing a graph. It can be translated into a 0-1 matrix. As a usual way, adjacency matrix. A 1 in the third position of the second row means that nodes number 2 and 3 are connected by an edge. Now this this is just another coding of this, so I replaced the ones by black squares and the whites and the zeros by white squares, and so I get this kind of crossword-like picture, which I call the pixel picture of the graph. So here is the pixel picture of an rendezvénye random graph with 100 nodes and 2,500 edges. So edge probability half. If instead of 100 nodes I would take maybe 10,000 nodes, then the picture would look like this uniform gray on the right-hand side, because there is no structure in it. And that's what is the uniform gray. You can think of it as a grayscale representation of the function on the unit square, where the value is 1/2 at each point, which is kind of the local density of the rendezvénye random graph. Now it's not exactly the Barabashi-Albert graph, but it's based on a similar idea, so it's also a graph which grows and adds a new node each time and then adds randomly some edges to it to keep the density fixed. And I call this randomly grown uniform attachment graph. It has 200 nodes. Now if you work out what happens if instead of 200 nodes you would do maybe 20,000 nodes, then you would see this picture on the right, which is 1 minus the maximum of x and y. That's the function. It's a very simple function. So for a very large value of the number of nodes, the picture simplifies, and eventually you just get 1 minus the maximum of 2 values. And that suggests to try to understand this limit process, that what happens if the number of nodes goes to infinity. Here I have shown a few of these such sequence of graphs where you expect to have some kind of interesting limit, or at least to have a limit. I mean, the complete graphs, any 2 nodes are connected. It's fairly clear that the limit will be just all black. Everything is there. Cycles is trickier. grids, larger and larger grids, or larger and larger hypercubes. These are all possible sequences where you might want to assign some kind of limit graph to it. And so all these sequences have this property that they are more and more similar. What does it mean, similar? They are less and less distinguishable. But how to distinguish two of these graphs? Well, you do statistical tests, just like it was done in the COVID case. You go far enough, pick a node, and look at what happens locally at that node. And this kind of statistical test, which has to be different for depending on how many edges the graph has, but I don't want to go into these technical details. So with these statistical tests, at least you can find that these sequences really should converge to something. But just to show you that this is not obvious, let's look at grids. Larger and larger pieces of the grid in the plane. What do you think is the limit? And well, I don't want you to raise hands, but if I do this, then half of you would say the infinite grid. I mean, obviously. The other half, maybe at least all physicists, would say that, oh, no, this is a finer and finer approximation of the continuously filled out unit square. So the limit is the unit square. And that's called the scaling limit in statistical physics. This is what our engineer from my introductory example would do. So think of more and more atoms arranged according to the same law, but smaller and smaller, and the limit, it will be a continuous object. Actually, the best answer is, and that I am just saying so that I complete the argument, it's the 1 by 1 torus where every point is connected in distance alpha one way and distance alpha the other way. Let's forget about this. So the rendezvénye random graph will converge to this identically 1/2 function, and these randomly grown uniform attachment graphs will converge to this function, the grayscale image of the 1 minus max xy function. These kind of limits I call a graphon, are called graphons. And you can prove that if a sequence converges under appropriate conditions, according to these statistical tests, then it has a limit. Now, this is only if the number of edges is large enough, a constant fraction of all pairs. Let me show you, just for fun, a really interesting example where the degrees are bounded. So this is the degrees of the graph. And graph so the number of edges is just linear in the size. So here are Penrose tilings. It's a well-known objects. They consist of two kinds of rhombi, which you can glue together, and you are not, some rule that you are not allowed to glue two, say, white rhombi in exactly the same position to each other. So that would make a twice that large rhombus, and that's illegal. And these Penrose tilings have this fantastic property that you can fill the whole plane with it if you want to. So it's tiled the whole plane, but there is no periodic tiling, so every tiling will look different at every particular point. So this is a very, very kind of surprising property, which has a lot of applications nowadays, but let me just stay with the basic thing. Now, this is my revenge for having to listen to all kinds of polysaccharides and these kind of things. So the limit of Penrose tilings, if you take larger and larger pieces, is a rhombic icosahedron, which is you stand on it, it's on one of the vertices, and you slice it through the other vertices. So these pentagons will be the slices are pentagons, and you connect two of them if the vector connecting them is parallel to an edge of the rhombic icosahedron. And so it's a beautiful picture going back to classic Greek geometry. Okay, let's come back. How much time do I have?
17 minutes.
Thank you. So let me come back to this question of existence of optima. We have looked at this problem, minimize x cubed minus cx minus 6x over x greater than equal to 0. We know that the minimum is attained at square root of 2. In particular, the minimum is not attained in rationals. So for a really traditional Greek philosopher, the minimum doesn't exist. Another way of what we could conclude is that real numbers are useful, because if once we extend the rational numbers to the real line, then this minimum can be computed. Let's look at another problem. Minimize the density of 4 cycles in a graph with edge density 1/2. So you have a graph where exactly half of the edges are present and half of the edges are missing. And you want to find 4 cycles, simply 4 steps which take you back to the starting point. And the question is, what is the density of 4 cycles? So if you start somewhere and make 4 steps, what's the probability that you get back to the starting point? And there is a theorem, actually going back to the work of Paul Eötvös, that this density is always strictly larger than 1/16. And it actually gets arbitrarily close to 1/16 for a very large random graph with edge density 1/2, but it can never be exactly 1/16. So it's always larger. However, the limit of these Eötvös-Rényi random graphs, the constant 1/2 graphon, which I have shown you, it assumes this minimum. So exactly as real numbers are useful if you want to solve minimization problems over numbers, real numbers, graph limits are useful if you want to find optimization problems, solve optimization problems over graphs. And this is a really simple optimization problem which you can ask. Now, in the last few minutes, I will start. I have to say something about our new work in this area. The graph limit stuff was done 20 years ago, so this is so it's interesting. You have a sequence of graphs which is convergent in this statistical sense, which itself can be different for dense graphs or small, sparse graphs. But then if you have a graph, then there are various structures that you can associate with this graph. And how does convergent is reflected on the structure of these things. So for example, matchings. We have talked about matchings, how to find the maximum matching. So what happens to the size of the maximum matching if the graph sequence is convergent? It converges, so that is fine. You can ask similar questions about colorings, flows, spectra of the adjacency matrix, about automorphism groups. And there is another structure associated, less well known, but also very important, which are matroids of the graph. So let me just come back to Borufska's work. So optimizing the check network, and he proved that the greedy algorithm always gives the exact optimum for this particular case. In order to prove this, you have to use some kind of properties of these trees that, these red edges form. We call it a tree, and so they don't never grow together, so they are always branching off. And he had to use certain properties of these. And these properties can be axiomatized, and that was done by Whitney. And it's not only that these properties can be axiomatized, but it turns out that these properties should be quite familiar, because they are exactly the same combinatorial properties as linear independence in a linear space, or algebraic independence, which is a more mathematical notion, and then these cycle-free edge sets in the graph, and all of these, and my interest will be in the rank function of this. He called these matroids, so that anything that satisfies these exchange properties. Now, the rank of a set is think of a matrix. The rank of a matrix is the maximum number of linearly independent columns of that matrix. It's basic linear algebra. And if I denote this by this R, a set, so the rank is at most the size of the set of columns. The first three are trivial. The fourth one is the interesting one. It is an inequality which relates the rank of the union plus the rank of the intersection to the sum of the ranks of the two sets. This is called submodularity, and that's what we have studied recently. Going back to Whitney, of course, this whole. And it has many applications in graph theory, combinatorial optimization, geometry, information theory, and so on. So matroids are a very central notion in many branches of combinatorics. So there is this matroid rank function, or submodular function, and that, of course, brings up, you have to define, if you want to see what happens to the matroid rank function for a convergent graph sequence, then you have to define convergence of these kind of submodular functions and limit objects. So what would be the limit object? Well, probably should be a submodular function, but not on the subsets of a finite set, but on the subsets of, say, the 0-1 interval or the real line, so on some huge infinite set. And so, of course, we have to develop a limit theory of submodularity, and so we have to allow infinite sets. And at that point, I began to search through the literature whether anybody has written already about these submodular functions on infinite sets. And here is the big surprise. And that's the title of of this slide. It's a tale of two communities. Choquet was a very famous mathematician. It seems that I have not. Okay. So Choquet was. He worked in 1945. He wrote a 160-page long paper about submodular functions, And then it has been followed up by a completely different line of research. And what is really, I think actually it's an embarrassing fact about the sociology of mathematical research, is that the matroid theorists, and not only matroid theorists, submodular function theorists in the combinatorial setting and in the analytic setting, had no idea about each other. There's no cross-reference between the two areas. Actually, I must say I found one cross-reference, and that's in a book of Alexander Scriber, whom we have elected yesterday as an honorary member. He wrote a 3-volume fantastic monograph about combinatorial optimization. Their showcase paper is cited, but only sort of mentioned, nothing more. So what is Choquet doing here? You look at a domain in, and I have also the devil here played. I mean, you see this square that should be an R, so it's R to the D, so that's the D-dimensional space. D could be 2 or 3 in practice. And so you take a domain in there, and for every subset of this, you would like to define what is the electric capacity of this subset. And the way it's defined is that you keep the outside at 0 level of potential, and then this little black thing is X in the middle, and so you want to put as much charge in there so that it generates an electric potential, so that this potential remains less than or equal to 1 in an appropriate measurement. And that's the capacity, that's the notion of a capacity. And of course, if this black area in the middle is sufficiently simple, and D is sufficiently simple, then this can be actually computed, this capacity, using partial differential equations describing the electrical potential. However, if this is getting more and more complicated, and for some reason he was interested in defining it to, well, for the mathematicians, for all Borel sets, the black could be any Borel set. So he wanted to extend this notion to larger families of sets, and that has been an unsolved problem in those days for decades, how to extend it to the electrical capacity. And then he showed that this electrical capacity is submodular, first for compact subsets, and then using this he defined a procedure to extend it. And so eventually it turns out that he solved the problem, and it's a fantastic paper. It has many other things which are cited, thousands of papers. So let me point out that Whitney, who invented matroids, was also a very famous mathematician. And nevertheless, so 2 famous mathematicians developed parallel theories, and it was not noticed. Now, let me remark, just a side remark, that you may think that this is so old that it cannot be relevant anymore. I mean, more than 70 years ago he wrote this. But in mathematics, that's not the case. I mean, anything can be relevant for a very, very long time, and often the relevance is not even recognized for a long time. Semiradis regularity lemma was considered for a long while that it's a very technical, difficult to understand, and probably it's just the original purpose, which was in itself very interesting, but I don't have time to go into this. But then after maybe 20 years, it turned out that it's the key to all algorithms, about almost all algorithms that deal with very large graphs. So there was no interaction. And that opened up for us a quite exciting possibility of working out the connections. And I mean, this is rather technical, it's an ongoing work. So it is, there are a lot of really interesting parallels, theorems that were proved in one of the lines and can be proved in the other line if you work hard. Interesting algorithms that come from both. So it is really quite exciting and fruitful just to try to see what are, how the two lines developed. Now this is my, of course, as a combinatorialist, I think that the combinatorial line developed more and is more important relatively, but probably an analyst would not agree with me. Now here is, I just quote a theorem that we proved, which says that indeed if you have to define convergence in an appropriate sense, again with some kind of statistical means. If there is a convergent sequence of submodular functions on finite sets, then there is a submodular function on the Borel sets of the 0-1 interval, such that the same tests can be performed on this submodular function, and the results of the tests on the finite functions converge to the result of the test. I don't have absolutely no intention to explain this, but I just wanted to point out that the proof of this theorem uses Choquet's main theorem in this paper, so really this kind of cross-fertilization. Yeah. I have 1 minute to go, where I wanted to list the names of those young collaborators, the ELTE and the Rényi Institute, who took part in this, or take part in this ongoing research. Thank you very much.
Thank you. Let me hand over the present that we chose for the plenary speakers. And I'm sure you'll appreciate it because it's a gömböc. This time from another porcelain manufacturing, Herend, from Hungary. And here's the diploma. The gömböc, for those of you who may not know, is actually, probably Professor Lovász could explain it better than I can. It's a set of equations that describes this geometrical form that can actually revert to its own shape all the time, its own position in space.
Yeah, it has only one equilibrium position.
Yeah. Okay. With that, we are moving on. Thank you very much. Our next speaker is Professor Pál Maliga from Rutgers University, who is also second as the co-chair of the American-Hungarian Association of Hungarian External Members, the AMAT, and he is from the section 4 of the Hungarian Academy of Sciences, which is the section on agricultural sciences. His talk title is Chloroplast Genome Engineering, History and the Road Ahead.
Well, thank you very much. It's my honor and privilege to present at this anniversary, the Academy's anniversary occasion, representing Section 4. And I will talk about chloroplast genome engineering, the objective of which is improve crop productivity. And I promised myself that I will use a slide that everybody will understand, including Section 1. And How do I go forward on this?
The white button, white button.
The white button, okay. White button. So this is the process that drives life, photosynthesis. So this is what everybody kind of should know, that photosynthesis is using sunlight to split water and release oxygen in the process. And below, you see the light reactions. There are different intermediates are generated, like ATP and also reducing power. And these intermediates are used to fix CO2 and generate sugar through the Calvin cycle. So if you go home and tell what you learned, and you are from section 1, you say, okay, I learned what is photosynthesis, how sunlight is used to actually make sugar and drive life. So where the process is taking place is chloroplast. So on the top you see a cell. There is a green thing on the left side, which is a chloroplast. And above is the mitochondrion, and to the right, at the bottom, is the nucleus. So if you look, this is a chart that shows how the chloroplast has evolved. So at the bottom, there is a photosynthetic bacterium that was engulfed by a cell and was carrying out photosynthesis there, but then it became an organelle because all the genes migrated to the nucleus. So when it started out at the bottom, it has 3,000 genes approximately, and now in today's plants, there are 3,000 genes which migrated to the nucleus, are transcribed there, translated in the cytoplasm, and then the proteins migrate into the chloroplast. So this free-living organism became part of a cell where photosynthesis is carried out, and this is a compartment where the genes which are now in the nucleus are actually imported and carry out the same function that we used to carry out in the photosynthetic bacterium. And what is typical, and this is what is like in the red on the right side, that the enzyme that carries out the photosynthesis, the Rubisco, like one subunit is encoded by the plastid genome, and multiple copies of the small subunit are encoded by the nuclear genome. So these two meet inside the chloroplast and assemble into a functional enzyme. So this is a typical arrangement when there is contribution from genes from the two different genetic compartments. And you will see that we actually use the same ideas. If you want to make changes inside the chloroplast, we placed genes in the nucleus, which would then find their way in the chloroplast to do their function. So what we engineer is a circular genome, which is depicted here or shown here. And the problem is that there is not one copy of this, but there are probably 1,000 or 10,000 copies in each cell. So really the trick, and this is something we solved back in 1990, how to selectively to change one copy and selectively amplify it to make it every copy the same, the way we modified it. And this is now like a later version from a 2022 review that shows on the left side that we are introducing a vector which has a part of the chloroplast genome, and then it carries a marker gene of the gene of interest. So we take a piece of the chloroplast genome, we cut it between two genes, we put in the marker gene and the gene of interest, and it becomes part of this larger circle. And so basically we keep these cells growing until every genome copy is changed. And when we have done what we wanted, then we can remove the marker gene, because in a commercial product, it would be unacceptable to have a marker gene. And this is accomplished by, we transform the nucleus with a site-specific recombinase that will cut out through the triangles on the right side the MG, which is the marker gene. It is cut out in every copy, and then we get a circle as a product of the excision. So basically, we can change the chloroplast genome. We can modify it by removing all the marker genes. And the process where we introduce and get this uniformly transformed chloroplast genome populations is based on a biolistic process which was invented in the late last century. We use a biolistic gun to propel gold particles into a leaf cell, which is like shown on the top. And then these gold particles are covered with DNA, and when they penetrate the cell, the DNA finds its way into the chloroplast or lodges inside the chloroplast itself and makes them tolerant or resistant to the antibiotic. So the antibiotic, which is in the medium, blocks translation of the plastic ribosomes. This is why they cannot green up. But when we express an enzyme which is detoxifying this antibiotic, then the chloroplasts which are in those cells can actually green up and can also regenerate into shoots. So basically, it's a complicated process to see how we can change thousands of copies and then generate a plant, but this is a sorting out process. And these plants that are shown in the plate where they just show up, these are typically having sectors of transformed and non-transformed chloroplasts. Then we chop this up and repeat the process, and in about 4 months, we get a plant in which every one of the genome copies is uniformly changed. And so I was showing you in an abstract how we make changes, and this is like a specific example on the top. You see there is the AADA gene. This is a spectromycin resistance gene, which is giving protection, basically modifies the antibiotics that they can no longer bind to the ribosomes. And what we see, there are those two arrows basically replacing what is marked here as an RPOB, which is the RNA polymerase gene. So then the plants which lack this RPOB gene, they lack an RNA polymerase. Basically, they cannot make any more proteins in the chloroplast ribosomes. So what you saw on the right side, these are completely white plants because they don't have chloroplast ribosomes functional anymore, but then they would have these green non-photosynthetic shoots that can be grown up. So this is the process that we developed and published in 1990. And whatever is in red is like routinely used for making changes, and every change is based on homologous recombination I was showing, and also by selection for spectromycin. So there is no rhyme or reason, basically, but the only way to engineer chloroplast genomes is using spectromycin selection to introduce foreign DNA, and then this can be done in plants where this process is working. So this process is, for example, not working in any of the monocots. It works well in potato or works in soybean or tomato, which are major crops, but for example, it's not working in any of the monocots. So this was going on from 1990, you see a timeline here, all the way to 2019. And so all organelle genome engineering was engineering the chloroplast genomes based on homologous recombination. And in 2019, there was a dramatic change. Suddenly, the chloroplast genomes and the mitochondrial genomes could be transformed in any crop. The reason is that people were not modifying directly the chloroplast DNA. Basically, if they could modify or transform the nuclear DNA, there is a way to send in nucleotide modifying enzymes, and nuclear gene transformation was available virtually for any crop, which meant that chloroplast genomes and mitochondrial genomes could also be modified. And so the pioneers of this were like professor at the University of Kyoto, Shinichi Arimura. And there is also a professor in Korea, Jin-Soo Kim, who developed this tail repeat-based engineering technology. And I'm not getting into this. I wrote a review in 2022 where I kind of discussed this. So this was a very major breakthrough, but these all have deficiencies. And the problem is that the changes cannot be really designed. So this is why we started to work on a technology which is based on what is shown on the right side using the CRISPR-Cas9 technology. So the idea is that we are using a variant of Cas9 which doesn't cut the double-stranded DNA. And when you see that arrow on the top, so the problem is that if you cut the double-stranded DNA in the chloroplast and also in the bacteria, it results in a large deletion, which are then repaired by microhomology-mediated recombination. This is technical, but if we cut the double-stranded DNA, basically we have a large deletion. And this can be avoided by a method that was developed in 2020, which is shown on the right side, which is called prime editing, where we cut only one of the two DNA strands, and then we provide a template for the repair. So the Cas9 is fused with the reverse transcriptase, and where you see the arrow, this is where the cut is. Then above this, we have a longer RNA that serves as a template for the repair. And on the left side, basically, we can accomplish the same by homologous recombination, but it's a tedious process. So we are basically looking for a better and more efficient way of putting in point mutations or deletions in the chloroplast genome. This is a current and ongoing work. I mean, the technical foundations were set up for this 2020. We adapt what is there, basically developed for bacteria in a plant version. On the top, we show a Cas9 gene that we fuse with a transit peptide. So when we put this gene into the chloroplast, then it will be transcribed there. The RNA moves to the cytoplasm, translated, and the protein is imported into the chloroplast. We show only one chloroplast. In real life, there is 100 or 120 chloroplasts, each of them having a total of 2,000 genomes to 6,000 genomes. So if you want to then modify, we have to also provide a guide RNA that would be directing the change. And for this, we developed the system where we make a mini gene that we also put into the chloroplast genome. So this is to test out the system, and this is where inside the chloroplast, the Cas9 protein meets the guide RNAs and then does what it is supposed to be doing, in this case, cutting the DNA.
If you want to use the pointer, there's a pointer.
Is there a pointer?
You can just point it to.
Oh, okay. Thank you. It's nice to have a pointer, if you know about it. Okay, so what you show here is, so we have a Cas9, and we wanted to be sure that this Cas9 is actually inside the chloroplast. So we fused it with the green fluorescent protein. So then we look under confocal microscope and we see that in the chloroplast, which are at the periphery of the cells in this particular cell type, then they coincide with the red fluorescence of the chlorophyll. So this means that the Cas9 that we engineered, which is actually a big protein, it ends up inside the chloroplast and it is localized there. Okay, so how do we check whether or not our Cas9 is active? As I said, we cut the DNA, and we were picking locations where we can actually study the deletions, because if the genes are lost, there is no phenotypic consequence. So we did this last century. If we remove MBH genes, which are localized like in this cluster, for example, then there is no phenotypic consequence. So we can test out our Cas9, we can make sure that it is not only there, but it is also working, and actually picks up the guide RNA and cuts where we want it to cut in the NDH cluster. So the problem with making the guide RNAs is that in the chloroplast, there is no efficient transcription termination. So if transcription starts, it keeps going through and never ends. And for a guide RNA, we have well-defined ends. And one end can be a promoter, which is initiating at the known site, but there is no known efficient transcription terminator. And for this, we were using actually the tRNA machinery, which are generated by two different RNases. The one that we were using is RNase-P. So what we did, we have the guide RNA, we have a tRNA, and we count on the processing via the RNase-P. And then we get our well-defined like guide RNA, which has a defined end because it initiates a transcription initiation site, and there is an RNase-P generated like processing at the 3' end. So when the small RNA from these plants was sequenced, we are looking at the output of 10 million reads. There are about 700 properly sized guide RNAs which are initiating at the transcription start site and are processed by RNase-P at the 3' end. So we have what looks like a well-defined RNA that we could make by using tRNA for processing. We also have ribozymes, we can do similar functions. Okay, so then is this Cas9 now is presumably picking up the guide RNAs, which are the right size. Does it do the cutting? And so the Cas9 carries a gentamicin marker. The mini-genes have a spectinomycin marker. And then we crossed the two and germinated the seed on spectinomycin, gentamicin. So basically, in these plants, we have the markers, which would mean that we have the Cas9 together with the guide RNA. And when we look at these plants, we see these pigment-deficient sectors, which are the workings of the Cas9 cutting the chloroplast DNA at the right place. This is somewhat complicated. As I said, if you cut the double-stranded DNA and we cut it here where the gRNA is, this is where the guide RNA is coming from. So there is a double-strand break, and then there is a chew back of the DNA, and it will be reconnected by homologous recombination. And in case of one of these, the repeat is in YCF1, is one of the essential genes, and the other end is in the NDHA gene. So the point is that in every DNA sample, you see smaller fragments because there are large deletions in this. And these are like flanking our target site. So what it means that basically, whenever we cut the DNA, somewhere it is restored by microhomogene-mediated recombination, but we get the change that we wanted to get. I also said that not every deletion results in a deletion that would result in the loss of an essential gene. So these are plants which have a large deletion in them, as shown here by the PCR, but they have no other phenotypes. But then we sequence the genome of these plants, and then we see the large deletion that we actually plant. So this is the cut site, the blue arrow points to the cut site, and then these plants actually have, based on the genome sequencing, like 2 large deletions. And many of them have no other phenotype, just the deletion at the right size. And so sometimes there is also a problem that the Cas9, which is still there, picks up an RNA from somewhere and randomly introduces a small mutation. So some plants only have the deletion that they are supposed to be having, but sometimes there is also like an off-target effect, as they say, when there are mutations that we're not planned for. So we are at the point that we have active Cas9s, and we have a Cas9 reverse transcriptase fusion, and now we are working on the implementation of this prime editing, where the template for the change is actually included in a larger RNA. And so with this we can introduce point mutations only that we were intended to do. And this is still an ongoing process, but so when right now we make our mini genes from the chloroplast genome, but we are working on how to make RNAs, guide RNAs, which are imported from the nucleus. So basically we can modify the chloroplast genome at great precision by transforming only the nucleus. So doing research and developing tools is like one activity, and I personally was involved in creating a forum for engineering chloroplast genomes, and this is a Gordon Research Conference on chloroplast biotechnology. And what you should know that there is about 360 different Gordon Research Conferences, annually about 180 because these are biannual. And whatever is discussed there stays among the participants. So the original idea was that at the Gordon Conference, which is kept small, cannot be bigger than, let's say, 200, that the scientists and industry can meet and then generate new ideas. So whatever is discussed there, it can be used, but it cannot be discussed. So the conference is there by now for 10 years. So the last was in 2025 in April, and I am the founding chair of this conference. And I can't tell you what was discussed, but I can tell you the kind of ideas that are being discussed or being explored. So one interesting fact is that so this is the utilization of the sunlight's energy. And the plants use 2 different biochemistry. One is called the C3 biochemistry, which is symbolized here by soybean, and the C4 biochemistry, which is corn. And one of them uses 4.6% of the incoming sunlight. The C4 biochemistry utilizes 6%. So there is a 30% difference between the C3 biochemistry and the C4 biochemistry. And this biochemistry is done by the Rubisco enzyme, where the difference is, if you look in the middle, you see that there is photorespiration. So the C3 plants do photorespiration, the C4 plants don't do any. So the efficiency is coming from the different biochemistry that the plants use. And so coming back to Rubisco here, so this is the enzyme in the middle, and Rubisco is doing two reactions. One is the carboxylation reaction, which was on the top and is associated with the green arrow. This is the reaction that generates the Calvin cycle and generates sugar. And there is an oxygenation reaction, which is using oxygen and results in the net loss of CO2 and the ammonium. So this is a process that works in the C3 plants, results in the loss of the fixed CO2 and also nitrogen. And this is a process that is missing from the C4 plants. So at the conference, okay, I finish. So basically, ideas were discussed that come from photosynthetic bacteria and algae. How can this process be avoided by the photorespiration by using adding additional enzymes to cycle to prevent the loss of this CO2 by photorespiration. The other idea is to teach plants to make their own nitrogen, and it takes like 18 genes to put this process from bacterium into another bacterium. But the plants already figured out that if there is an alga which has two plastid-like structures. One is a chloroplast that we discussed, and this alga picked up another variant from a nitrogen-fixing bacterium, which made it into an organelle. So this alga can fix sunlight, and at the same time can use fix nitrogen. So it's like a template how to make nitrogen-fixing plants. And I mean, whatever I wasn't telling you, or it didn't have a citation at the bottom, is basically new work. And this is the work of like two postdocs here. Corinne Best came from Israel, wanted to say, why don't we engineer mitochondria? I said, okay, why don't we just do chloroplast first? That is more simple. We started this 2021, and the other hero of this, like Maliga and other postdocs, so who are co-inventors on the patent application. And the funds come from NSF Plant Genome Program, also BARD, the US Israeli Binational Science Foundation, also from Rutgers. And we also have 2-3 undergraduates who are very enthusiastic. One of them is here, who works on RNA import into chloroplasts. And I stop here. Thank you.
Thank you very much. Professor Maliga, let me hand you over this. Thank you very much. Thanks. With that, we conclude the morning session and my chairmanship of this session. We are having lunch and an hour and a half. So please reconvene here promptly at 2 p.m. under the new chairmanship of Dr. Eva Mezei, who is from the intramural program of the NIH.
I have one more thing to do, and that is to thank István for organizing and running the session.
Thank you. My pleasure. Thank you.